right, so now something pretty important. You'll see this in various questions. For a sphere, our parameterization is g of theta phi equals the following. And we have an r cosine theta sine phi, r sine theta sine phi, and an r cosine phi. Okay? So when we take the tangent vectors, I'll do that here. So tangent with respect to phi is going to be, so if we differentiate here with respect to phi, so we're looking at the sine theta here, then we get r cosine theta, cosine phi, right? These are just constants. The second component, if we're looking at phi, is just, these are the constants and we're differentiating that. So we have r sine theta and a cosine phi again. And then the last one, we have a negative r sine phi. Okay? And then the other tangent vector here with respect to theta is now we're looking at the theta as the variable. So we have r, a negative r sine theta, and then a sine phi, that's just a constant, so that stays the same. And then we have an r cosine theta, right? R cosine theta sine phi. And in the last component, we don't have any thetas, so that's just going to be 0. All right? So what I'm going to do here now is pretty important because, well, you might actually, I know there's a problem in the book somewhere that exists where you have to prove what the normal vector is when you cross these two. And it's doable. It's just kind of tedious. But I'll show you here that, I'll tell you here that the normal vector when you cross these two and set up the whole like I, j, k thing, that's just going to equal r squared sine phi times the following. Cosine theta sine phi, and then a sine theta sine phi, and a cosine phi. So what this essentially means is that this here, everything in the vector form right here, technically that, like, people call it the unit radial vector. So that means unit, first of all, so this is your unit radial vector. Okay, so unit means 1. It has a length of 1, so the length of the vector part here, again, we're not considering this yet, but just everything in the arrow brackets. So the magnitude, I'll just write magnitude of E sub n, equals 1. Sorry, I'm squishing it in over there. So the length of this thing is 1, and that's pretty much the important part here. And so anyways, what that signifies is that when we look at the normal vector equaling this, sorry if you hear dogs in the background. My neighbors have dogs and they're really loud. So if you take the norm of this, or the magnitude of n, what we're going to get is r squared sine theta times 1. Okay, so that's pretty important as far as surface integrals go. And this is, so like I said, that's pretty important if you don't want to derive that every single time that you do a problem involving spherical coordinates or anything like that, or spherical parameterizations. Okay? Alright, so now let's go on to, we're getting it more into the surface integral part, we'll start with surface area. Okay? So now that we have the foundation of what a normal vector is and how to calculate it from the tangent vectors, then we can tackle this. So basically, let's say we have some surface, right? So I'll just draw like a little patch of a surface. So something like that. And here's our tangent vector here, and our tangent vector here. Okay. So this is like our, this is t sub u. And technically it's times the change in u as well. That's just a technical thing. If you want to see the real derivation of it, you can always look it up in your book. But that's what it's equal to, the tangent vectors here. Because this is when v is constant, right? So this is when v is constant. These are our grid curves, remember? The tangent line along the grid curves. And then this is when u is constant. U is constant. Okay, so basically what happens is that the the estimated surface area of this little patch here, this patch of the surface, so this part right there, the estimated surface area, so estimated, I'll just abbreviate, surface area is the following. So area of S, which this is S, this little patch, is equal to the double integral over d, and I'll specify what all of this means, of the magnitude of the normal vector, and then du dv. Okay, so what this means is that the d is in reference to the parameter domain of u and v. Okay, and this, so that's what that means, is basically on our two integrals here, the bounds will be like u goes from 0 to 1, or v goes from 0 to 2, or something like that. And from the previous explanations, we know what the normal vector is, and here we'll just take the magnitude of it. So this is just magnitude of normal vector. Normal, and I'll just put like a little vector sign. Okay? And then du, dv are just there as differentials. Okay? So now we can get started. So this is for surface area. Again, this is just to find how big, or the surface area, the area of the surface of a given surface. I don't know how to say that in any other way. So now we'll go on to surface integrals. So surface integrals, and these are a little bit different from surface area. Surface integrals. Oop, I am moving the screen, but it's not good. Okay, so surface integrals. What this is going to look like is, well, first of all, this is going to be scalar. Okay, these are the scalar kind. In a future video, we'll go over vector surface integrals, but right now we're going to deal with the scalar kind. So we're dealing with some function of x, y, and z. This is a scalar function as well. Okay, so what we're going to have is, this is the notation of it. Y and z, and then d capital S. Okay, so this signifies surface integral over the surface S of this scalar function. Okay, so what this is equal to is the following. And again, I'll explain all of this as we go through. So g of u and v, and then times the magnitude of the normal vector, okay, and then du dv. Okay, so what this means here is that we're going, d again, that's of u and v, so that's the domain of the uv plane, right? And then g of u and v, so this here might look a little bit confusing, but it's basically like a composition of functions. So our f is of x, y, and z, right? And our g gives us some coordinates in u, or in x, y, and z, but each one of them depend on a u and v in some way. So what this is going to look like, so f of g of u v looks like some kind of, it's basically like this. So we have some kind of f of x of u and v, f of y of u and v, and z of u and v. So again, it's kind of hard to maybe like decipher or interpret just writing in like variables and stuff, but when we do concrete examples, it'll make perfect sense, hopefully. So okay, and then we already know what this is. This actually gave us the surface area, right? But we know how to calculate the magnitude of the normal. Okay, and then one other thing is the special case. So special case, when our f of x, comma y, comma z equals a positive 1. Because in that case, then we have the following, d of 1 times n normal, magnitude of the normal, and then du dv, and this should look similar to the previous slide, right? And this gives you your area, or your surface area of S. Okay, so that's when f of x, y, z equals 1. All right.